What are dark matter and dark energy? These two mysterious forces make up over 95% of the universe, but their nature is still one of the great mysteries of modern science. Scientists know they exist because of their effects on gravity and the expansion of the universe, but what are these forces? And how do they shape our cosmos? In this video, we'll delve into the mysteries of dark matter and dark energy, the invisible forces that determine the fate of the universe. Dark matter. What is it? Let's start with dark matter. Despite its name, dark matter has nothing to do with dark in the usual sense. It is an invisible substance that does not emit, absorb, or reflect light, so we cannot see it directly. But how do we know it exists? It all comes down to gravity. When scientists observe the movement of galaxies, they notice that visible matter, stars, planets, and gas can't explain the observed force of gravity. Without dark matter, galaxies could not rotate at such speeds, and many of them would simply disintegrate. This suggests that invisible mass, which we can't observe, has a huge influence on their structure and behavior. Dark matter plays a key role in creating the universe as we know it. Scientists believe that it was its gravitational pull that helped form galaxies and large structures in the universe after the Big Bang. Without its presence, matter would not have been able to clump together in such dense formations. Galaxies, including our Milky Way, exist because of dark matter. It surrounds them as an invisible halo, holding stars and other objects together. Without this invisible framework, galaxies simply couldn't be held together. While dark matter is the invisible force holding galaxies together, dark energy acts in the opposite way. It is responsible for the accelerated expansion of the universe. In 1998, scientists made a shocking discovery. Not only is the universe expanding, but it is doing so at an accelerating rate. This process cannot be explained by gravity or known forces. Dark energy, according to scientists, is the mysterious force that opposes gravity and pushes galaxies apart. Imagine galaxies are like pieces of dough in a yeast cake, and the more time passes, the faster that dough stretches. Dark energy determines the future of the universe. If it continues to accelerate, galaxies will move away from each other faster and faster. This will lead to a scenario that scientists call the Big Rip. Eventually, all matter, including stars, planets, and even atoms, could be torn apart. However, until we fully understand the nature of dark energy, the future of the universe remains uncertain. Some hypotheses suggest that dark energy may change or even disappear in the future, slowing the expansion of the universe. But until that happens, the universe will become increasingly rarefied and colder. But how do scientists study these invisible forces if they can't be seen directly? In the case of dark matter, they observe the gravitational effects on other objects. Scientists are also conducting experiments in underground laboratories, trying to catch dark matter particles passing through the Earth. However, all attempts so far have failed to yield definite results. Dark energy is studied through observations of supernovae stars and relic radiation. These observations help scientists measure the rate of expansion of the universe and try to understand how and why that rate is increasing. Dark matter and dark energy are some of the biggest mysteries of modern science. Together they make up 95% of all matter and energy in the universe, but we still don't know what they are. Despite decades of research, scientists are only beginning to understand how these invisible forces affect our cosmic environment. However, with each new discovery, we're getting closer to understanding how the universe works and what the future holds for us. If you've been curious about these mysteries, don't forget to subscribe to our channel so you don't miss new exciting videos about space and science.
The universe is an endless mystery filled with amazing objects and physical phenomena beyond our understanding. Black holes, relic radiation, dark matter, and dark energy all hide clues to the fundamental laws of the universe. Today, we will dive into the world of astrophysics and cosmology to find out what secret space-time hides and what incredible discoveries await us in the future. Black holes, traveling beyond the event horizon. What is a black hole? A black hole is a region of space where gravity is so great that even light cannot escape its confines. Inside it is the point of singularity, where, according to the general theory of relativity, matter shrinks to infinitesimal size. But what happens beyond the event horizon? Can information trapped inside a black hole ever escape, or does it disappear forever? The quantum nature of black holes. Modern physics looks at black holes not only through the lens of gravity, but also from the perspective of quantum mechanics. Here are a few key hypotheses. The holographic principle. The theory states that all information entering a black hole does not disappear, but is stored on its event horizon in the form of a two-dimensional quantum code. This could mean that the three-dimensional universe is actually a hologram projected from the boundaries of space. Hawking radiation. Stephen Hawking proposed that black holes can slowly lose mass and evaporate due to quantum effects. This discovery overturned ideas about the thermodynamics of black holes. Mole holes. Some hypotheses suggest that black holes may be portals to other parts of the universe, connecting different regions of space-time. Relic radiation. Echoes of the Big Bang. Relic radiation is the weak microwave radiation left over from the Big Bang. It contains information about the first moments of the universe's existence. How was it discovered? In 1965, Arno Penzias and Robert Wilson accidentally detected this signal while investigating the cosmic background. It became one of the most important pieces of evidence for the Big Bang model. What does it tell us? Relic radiation reveals the tiny fluctuations in temperature that formed the first structures in the universe: galaxies, stars, and black holes. A link to quantum gravity. Some hypotheses suggest that traces of the quantum fluctuations that existed in the first moments after the Big Bang can be detected in relic radiation. This discovery would help unify quantum mechanics with gravity. Dark matter and dark energy. Dark matter, an invisible substance. Ordinary matter, which makes up stars, planets, and humans, makes up only 5% of the mass of the universe. The rest is dark matter, 27%, and dark energy, 68%. Dark matter does not emit light or interact with the electromagnetic field, but its existence is confirmed by gravitational effects. It keeps galaxies from disintegrating. Its presence is revealed through gravitational lensing. Dark energy. What's accelerating the expansion of the universe? Dark energy is the mysterious force responsible for the accelerated expansion of the universe. It was discovered in the late 1990s by observing supernovae of stars. Future of the universe. Various scenarios predict the fate of the cosmos. The Big Freeze. The universe will expand indefinitely, the stars will fade away, and the cosmos will become a cold void, the Great Divide. If dark energy intensifies, it will tear even atoms apart. Great Compression. Gravity could stop the expansion, and the universe would collapse backwards. Archaeology of the universe. The search for ancient galaxies. The James Webb Telescope has already made it possible to peer into the depths of space and see galaxies that existed just 200 million years after the Big Bang. Ultra-diffuse galaxies. Scientists have recently discovered strange galaxies, such as NGC 105 to DF2 and DF4, that are virtually devoid of dark matter. This discovery calls into question standard models of galaxy evolution. Current space research. Gravitational waves. In 2015, the LIGO Observatory recorded gravitational waves vibrations of space-time caused by merging black holes for the first time. Quantum simulations. Scientists are now using quantum computers to simulate extreme cosmic conditions. These experiments help test hypotheses about black holes and quantum gravity. Historical perspective. Ancient science and the universe. Our understanding of the universe is based not only on modern research, but also on the legacy of great thinkers of the past. Archimedes and ancient calculations. Archimedes is known to have created mechanisms to predict astronomical phenomena. His work may have inspired the creation of the Antikythera mechanism, an ancient device that used a complex system of gears to calculate the motion of the planets. Babylonian astronomical cycles. The ancient Babylonians observed the movements of the planets and developed the Saros cycle, an 18-year period that allowed them to predict solar and lunar eclipses. This knowledge became the basis for future scientific discoveries. The philosophical aspect. Where are the limits of reality? Modern discoveries lead to important philosophical questions. Do parallel universes exist? Is it possible to surpass the speed of light? Could our perception of reality be an illusion caused by quantum effects? These questions are not just hypothetical, they raise the foundations of science itself. Each new discovery in cosmology raises more questions. We are just beginning to unravel the mysteries of black holes, dark matter, and quantum gravity. But one thing is certain. Science is an endless journey, and the most amazing discoveries are still waiting for us. Subscribe so you don't miss new videos about the mysteries of the universe.
What if I told you that what we see in the universe is only a small part of reality? All the visible matter we observe, stars, planets, galaxies, is only 5% of the universe. But what about the other 95%? Here begins the story of the two greatest mysteries of the cosmos, dark matter and dark energy. Dark matter is a mysterious substance that cannot be seen directly. It does not emit or reflect light, and therefore cannot be observed with modern telescopes. But then how do scientists know it exists? The answer lies in the gravitational influence of dark matter on visible objects. For example, the rotation rate of galaxies indicates that there must be more mass in them than what we see. This indicates that there is invisible dark matter holding galaxies together, like an invisible hand. Dark matter is thought to make up about 27% of all matter in the universe. It forms a kind of skeleton around which galaxies are built, and without it, our universe would look very different. Now let's talk about dark energy. This even more mysterious force makes up about 68% of the universe's energy. It is dark energy that is responsible for the accelerating expansion of the universe. Imagine this: if you threw a ball upwards, and not only would it not stop at the peak, but it would begin to accelerate in its ascent. This is what is happening to the universe. It continues to expand, and dark energy appears to be driving this process. The discovery of dark energy was a real surprise to scientists. In the late 1990s, researchers expected gravity to slow down the expansion of the universe. But instead, they found that the universe was accelerating in its expansion. This discovery forced scientists to rethink their ideas about the cosmos and wonder what this invisible force was. Dark matter and dark energy are two of the greatest mysteries of modern astronomy and physics. They determine the structure and future of our universe, but they remain virtually unfathomable until now. Perhaps someday we will be able to unlock their secrets and understand how our universe works at the deepest level. If you're interested in learning more about the mysteries of space, don't forget to subscribe to the channel and give us a like. Together we will continue to explore the greatest mysteries of the universe.
The cosmos is full of mysteries, but some objects in the universe truly challenge our understanding of the laws of physics. What happens inside a neutron star? Can the universe survive its own end and be reborn? What happens to matter at the event horizon of a black hole? Let's explore these extreme phenomena in depth. The secrets of neutron stars. What is a neutron star? A neutron star is one of the densest objects in the universe, formed after the explosion of a massive star as a supernova. Once the fuel for nuclear fusion in the star's core is exhausted, its outer layers are ejected into space, while the remaining core collapses under the force of gravity to an incredibly high density. As a result, an object with a diameter of about 20 kilometers is created, but with a mass exceeding that of the Sun. Physics inside a neutron star. Extreme density. A teaspoon of neutron star material would weigh billions of tons. The matter is so compressed that electrons and protons merge to form neutrons. Quantum effects. Due to the Pauli exclusion principle, neutrons cannot occupy the same quantum state, which creates what is known as neutron degeneracy pressure, preventing further collapse. Superconductivity and superfluidity. The inner region of a neutron star exhibits exotic properties, such as superfluidity absence of viscosity and superconductivity absence of electrical resistance. Types of neutron stars. Pulsars rotating neutron stars that emit powerful radio waves, which can be detected on Earth. Magnetars neutron stars with incredibly powerful magnetic fields, trillions of times stronger than Earth's. Strange stars, a hypothetical type of neutron star where matter may exist in the form of so-called strange matter, composed of quarks. What happens if a neutron star gains mass? If a neutron star continues to accumulate matter, for example, from a companion star in a binary system, its mass may exceed the Tolman-Oppenheimer-Volkoff limit, about 2.16 solar masses. In this case, gravitational pressure becomes so strong that the neutron star collapses further, transforming into a black hole. The Big Bounce theory, the end or the rebirth of the universe. Cosmological scenarios for the future of the universe. Big Freeze, the universe continues expanding indefinitely, eventually reaching a state where temperatures approach absolute zero. Big Crunch, gravity takes over, causing the universe to collapse back into a singularity. Big Rip, dark energy accelerates the expansion, tearing apart galaxies, stars, and even atoms. Big Bounce, after collapsing, the universe experiences a new birth, leading to another expansion phase. How does the Big Bounce theory work? According to this theory, the universe undergoes cycles of expansion and contraction. When density reaches a critical threshold, the laws of quantum mechanics may prevent infinite compression, triggering a reverse explosion, a new phase of expansion. This suggests that our universe might be just one of an infinite series of cosmic cycles. Evidence and hypotheses. Quantum gravity. Some theories, such as loop quantum gravity, suggest that quantum effects prevent the formation of a singularity. Cosmic microwave background radiation. Anomalies in the relic radiation may contain traces of a previous cosmic cycle. Dark matter and dark energy. Their properties could be linked to remnants of a previous universe cycle. Observations of galaxy distribution. Modern astronomical studies, such as large-scale structure mapping, may reveal deviations indicating a cyclic nature of the cosmos. Gravitational waves. Analysis of signals from black hole mergers using LIGO and Virgo detectors may provide insights into the nature of gravity under extreme conditions. Experiments on quantum gravity modeling. Laboratory experiments using curved space-time analogs allow researchers to explore potential scenarios of the Big Bounce. Journey to the event horizon of a black hole. The holographic principle and information preservation. One of the most fascinating hypotheses related to the event horizon is the holographic principle. According to this theory, information that falls into a black hole does not disappear without a trace, but is instead encoded on its event horizon. This means that even though an object is lost inside the black hole, its quantum state remains preserved as a holographic imprint. This principle is a key area of research in modern quantum gravity studies. What is the event horizon? The event horizon is the boundary beyond which not even light can escape the gravitational pull of a black hole. This means that any information beyond this boundary becomes inaccessible to external observers. What happens to matter at the event horizon? Time dilation effect. To an outside observer, an object falling into a black hole appears to slow down and never actually crosses the event horizon. Spaghettification. Tidal forces stretch an object along the direction of its fall, turning it into a spaghetti-like structure. The information paradox. Classical theory suggests that all information about the falling object is irreversibly lost, but quantum mechanics requires that information must be preserved. Possible ways to bypass the event horizon. Modern mathematical models consider several alternative solutions to the event horizon problem, including the possibility of information preservation and escape mechanisms. Holographic principle. According to this hypothesis, all information that enters a black hole does not vanish, but is recorded on its event horizon. This suggests that three-dimensional information can be encoded on a two-dimensional surface, preserving key data about absorbed objects. Quantum gravity and loop theory. Some models of loop quantum gravity propose that instead of a singularity inside a black hole, a quantum structure may exist that prevents complete collapse of matter. This could allow information to be preserved and potentially escape. Adds or CFT correspondence. In this approach, black holes can be described through quantum field theory without gravity, allowing for interactions at the event horizon and their possible evolution. Firewall hypothesis. A controversial theory suggesting that a high-energy particle barrier forms at the event horizon, destroying information before it enters the black hole. This contradicts the principles of quantum mechanics and remains a debated hypothesis. Wormholes and quantum tunneling. Some models suggest that information could move through space-time, escaping from the black hole via a wormhole connected to another region of the universe. These models continue to be studied within the frameworks of modern quantum gravity theories and general relativity, helping to shed light on fundamental questions regarding the nature of the event horizon and the fate of information. Other possible escape mechanisms. Through wormholes. If black holes are connected to other points in the universe, matter could travel through them into different regions of space-time. Hawking radiation evaporation. Due to quantum effects, black holes gradually evaporate over time, potentially releasing stored information. Multiverse theory. Under extreme conditions, matter could cross the boundaries between different universes. Connection to quantum gravity. Some theorists suggest that information might be preserved on the event horizon in the form of quantum excitations. Modern studies, including those related to quantum gravity and string theory, propose possible resolutions to the information paradox. The firewall hypothesis, for instance, suggests that information does not enter the black hole, but instead disintegrates at the event horizon. Other theories, including adds or CFT correspondence, propose that information about the black hole's state might be encoded in an equivalent non-gravitational quantum theory at its boundary. The cosmos is a stage for the most extreme phenomena, challenging our current understanding of physics. Neutron stars are ultra-dense remnants of supernova. Black holes mark the final collapse of matter, and the universe itself may undergo cycles of death and rebirth. New research in astrophysics, quantum gravity, and cosmology is helping to uncover these mysteries, bringing us closer to understanding the fundamental laws of the universe. What is the event horizon? The event horizon is the boundary beyond which not even light can escape the gravitational pull of a black hole. This means that any information beyond this boundary becomes inaccessible to outside observers. What happens to matter at the event horizon? Time dilation effect. To an external observer, an object falling into a black hole appears to slow down and never actually cross the event horizon. Spaghettification. Tidal forces stretch an object along the direction of its fall, turning it into an elongated, spaghetti-like shape. The information paradox. Classical theory suggests that all information about the falling object is irreversibly lost, but quantum mechanics insists that information must be preserved. Possible ways to escape beyond the event horizon. Through wormholes, if black holes are connected to other points in the universe, matter could travel through them into different regions of space-time. Hawking radiation evaporation due to quantum effects. Black holes gradually evaporate over time, potentially releasing stored information. Multiverse theory under extreme conditions. Matter could cross the boundaries between different universes. The cosmos remains a vast and mysterious frontier, hosting some of the most extraordinary and mind-bending events in the universe. From neutron stars and black holes to the possibility of cyclic universes, our understanding continues to evolve. Breakthroughs in astrophysics, quantum gravity, and cosmology are constantly bringing us closer to deciphering these profound cosmic mysteries, pushing the limits of human knowledge.
Dark matter is one of the most mysterious and intriguing topics in modern physics and cosmology. Despite decades of research, its nature remains undiscovered, and its presence and influence are felt throughout the universe. Let's explore what dark matter is, why it is so important, and how it affects the structure and evolution of the cosmos. What is dark matter? Dark matter is a hypothetical form of matter that does not interact with electromagnetic radiation, which means it cannot be seen directly. Its presence is only established through the gravitational effects it has on visible matter such as stars, galaxies, and galaxy clusters. Key features of dark matter. Invisibility. Dark matter does not emit, absorb, or reflect light. Gravitational influence. It interacts with ordinary matter only through the force of gravity. Prevalence. Dark matter makes up about 27% of the total mass energy of the universe, while visible matter makes up only about 5%. Discovery and proof of existence. The idea of the existence of dark matter emerged in the early 20th century. One of the first scientists to point out its presence was the Swiss astronomer Fritz Zwicky. In 1933, he studied the velocity of galaxies in the Veronica Hare cluster and found that the apparent mass was not enough to explain their orbital velocities. He hypothesized that there must be invisible mass in the cluster. Later in the 1970s, American astronomer Vera Rubin studied the rotational curves of galaxies and came to similar conclusions. The velocity of stars at the periphery of galaxies appeared to be too high to be held together by the gravity of visible matter alone. This confirmed the presence of something invisible creating additional gravity. Further evidence. Relic radiation. Studies of the microwave background of the universe left over from the Big Bang also support the existence of dark matter. Gravitational lensing. Invisible mass alters the path of light, distorting images of distant objects. Numerical modeling. Computer simulations of galaxy formation and large-scale structures of the universe show that without dark matter, their formation would be impossible. Characteristics and candidates for dark matter. Despite the large amount of observational evidence, the nature of dark matter remains unknown. The main hypotheses include WIMPs, weakly interacting, Massive particles. These are hypothesized particles that interact weakly with ordinary matter. WIMPs are actively searched for using particle detectors. Sterile neutrinos. These are more massive and weakly interacting versions of neutrinos. Actions. Hypothetical particles propose to explain some anomalies in quantum chromodynamics. Modifications of gravity. Some scientists speculate that instead of dark matter, there may be an unknown form of gravity that manifests itself on larger scales. The role of dark matter in the cosmos. Dark matter plays a key role in the formation and evolution of the universe. Its influence can be divided into several main aspects. Formation of galaxies. Without the gravitational influence of dark matter, the density of visible matter would not be sufficient for the formation of galaxies and star clusters. Dark matter acts as a skeleton on which visible matter is assembled. Large-scale structure of the universe. Dark matter forms the threads that connect galaxies and galaxy clusters into what is known as the cosmic web. It is through its gravity that we observe these structures. Gravitational lenses. Dark matter creates effects that bend light from distant objects, allowing scientists to see its distribution, slowing the expansion of the universe. In the early stages of the universe, dark matter slowed its expansion, competing with the effect of dark energy, which, in contrast, speeds it up in later stages. Current research and experiments. The study of dark matter is being conducted on several fronts at once. Space telescopes, missions such as ESA Euclid and NASA Roman are designed to study the distribution of dark matter through gravitational lensing. Ground-based detectors, experiments such as Xenon 1T and LUX Zeppelin attempt to register dark matter particles. CERN, the Large Hadron Collider, LHC, is searching for new particles that may explain the nature of dark matter. Astrophysical observations, studies of relic radiation, galaxy distribution, and stellar motion are helping to clarify its properties. Mysteries and challenges. Although science has made significant advances in the study of dark matter, many unresolved questions remain. Why can't it be detected directly? All attempts to record dark matter particles have so far failed. What is its exact nature? Is it a particle, a field, or something completely unknown? How does it interact with dark energy? The interaction of these two mysteries of the universe remains a mystery. Significance to understanding the universe. Dark matter doesn't just complete the picture of the cosmos, it is at the heart of understanding it. Without it, it would be impossible to explain how galaxies formed, why the universe has such a structure, and what processes occur on large scales. Its study brings us closer to answering fundamental questions about the nature of the universe. Dark matter is the invisible architect of the universe. Its mysterious nature makes scientists search for answers, develop new theories, and conduct unique experiments. Each new discovery brings us closer to unraveling this cosmic mystery, and thus to a deeper understanding of the very essence of the universe. In my opinion, the study of dark matter is one of the most exciting and promising areas of modern science. It forces us not only to expand our understanding of the universe, but also to revise the fundamental laws of physics. Each step in its study is a step towards understanding how reality works in its deepest aspects. Therein lies not only the scientific, but also the philosophical value. If you enjoyed this journey into the world of the mysteries of the cosmos, don't forget to subscribe so that you don't miss new interesting materials. Thank you for your attention and see you in the next issues. Its mysterious nature makes scientists search for answers, develop new theories, and conduct unique experiments. Each new discovery brings us closer to unraveling this cosmic mystery, and thus to a deeper understanding of the very essence of the universe.
When you think of the North Pole, it's hard to imagine that it could switch places with the South Pole. How would this affect our lives? Imagine that magnetic compasses start pointing in the opposite direction, maps need updating, and birds lose their ability to migrate. Is that possible? As it turns out, yes. Geomagnetic upheavals have happened in the past, and they involve changes that could be far more dangerous than they first appear. Let's understand this phenomenon and try to answer the main question: should we be worried? How does the Earth's magnetic field work? Where does our planet's magnetic field even come from? If you look at neighbors in the solar system, such as Mars and Venus, it becomes obvious that a magnetic field is not a guarantee for the planet. Earth owes its magnetic shield to a liquid outer core made up of iron and nickel. The movement of these materials creates electric currents, which in turn generate a magnetic field, an effect known as the geodynamo. Question to ponder: why does the Earth have such a stable magnetic field while other planets lack one? The magnetic field protects us from solar radiation that would damage DNA, cause mutations, and threaten life. Without it, Earth could face conditions similar to the surface of Mars, where cosmic radiation constantly attacks the soil. In addition, the magnetic field plays an important role in the formation of auroras, which are not only a beautiful natural phenomenon, but also an indicator of the Earth's interaction with the solar wind. However, this process is unstable. Our magnetic field is constantly vibrating, and the North Magnetic Pole is moving. Since 1831 it has moved 1,100 kilometers towards Siberia. Interestingly, the speed of this movement is increasing from 16 kilometers per year to 55 kilometers. The Earth, despite its stable processes, faces constant change. One of the key factors providing the magnetic field is the presence of a liquid outer core that interacts with a solid inner core. This dynamic creates a flow of electrically charged particles, which generates the magnetic field. What are geomagnetic flips? Geomagnetic flips are reversals of the north and south magnetic poles. Scientists have found that such events have occurred 183 times in the last 83 million years. Sometimes 40 million years pass between coups, and sometimes just a few 100,000. The last coup occurred 750,000 years ago, making us indebted to the new event. Why do such upheavals occur irregularly, and what causes them? The main hypothesis links the overturns to changes in motion in the Earth's core. These changes can be caused by processes in the mantle, by interactions between the outer and inner cores, or even by large external impacts, such as asteroid impacts. Modern satellite studies are helping scientists better understand the dynamics of these processes, although much remains a mystery. During a flip, the magnetic field becomes chaotic and its strength can drop by up to 10% of its current level. This temporary weakening raises many questions about how such changes might affect life on Earth. Scientists can track the overturns thanks to layers of magma that solidify with an iron orientation that indicates the direction of the magnetic field as they cool. These data show that overturns can be both short-lived and long-lasting. Potential consequences. At first glance, it appears that magnetic pole reversal is merely a geophysical phenomenon. However, weakening the magnetic field in the process can have significant consequences. Solar radiation. A weakened field will lead to increased radiation levels on the planet's surface, affecting human health and ecosystems. A weaker field will be less effective in reflecting the solar wind, which could cause DNA damage and an increase in cancer. Satellite problems. Satellites will be jeopardized by inadequate protection from solar particles. This will lead to failures in communications, navigation, and other technologies. For example, the South Atlantic anomaly is already posing risks to spacecraft flying over the region. Power grids. Power grids will become vulnerable to solar storms, which could cause global blackouts. Solar flares could short-circuit electrical systems and knock out large transformers. Climate change. Studies have linked temporary fluctuations in the magnetic field to climate change and mass extinctions. For example, in Australia 40 to 1,000 years ago, such an event could have led to the extinction of giant animals such as diprotodons and giant kangaroos. Is it possible that in the future humanity will be able to predict such upheavals and minimize their effects? Geomagnetic upheavals are an amazing example of how complex processes within our planet can affect all of humanity. Although the likelihood of catastrophic consequences is low, the weakening of the magnetic field raises questions about our preparedness for such changes. I believe we must continue to study this phenomenon, develop defense technologies, and be prepared for the possible consequences. Understanding magnetic upheavals is not just a scientific interest, but a key to our future. Do you think current technology will be able to meet the challenges that may arise in the event of another coup? The Earth's magnetic field is our protective shield against cosmic threats, and its dynamics play an important role in preserving life on the planet. Its unique structure and ability to self-repair make it one of the main reasons why the Earth remains habitable. From small field fluctuations to possible upheavals, it all reminds us how fragile life on our planet is. However, with our level of knowledge and technology, we are able to face the challenges that nature poses to us. Let's continue to explore the mysteries of magnetic fields to prepare ourselves for any changes that may occur. Don't forget to subscribe to our channel for more fascinating information about our planet and the cosmos.
$13.8 billion years ago, an event occurred that changed the course of time and space forever, the Big Bang. It was the moment when our universe was born, filled with stars, galaxies, and eventually our planet. But what do we really know about those first moments? How did everything around us emerge from a tiny, incredibly dense state? Let's look deeper into this amazing story. What is the Big Bang? The Big Bang is not an explosion in the usual sense, but an expansion of space that began from a state of singularity, a point of infinite density and temperature. It was the moment when matter, energy, space, and time began to exist. The Big Bang event was the beginning of everything from the smallest particles to vast galaxies. The primary stages of the Big Bang. Planck epoch, 0 to 10 to the power of -40 for seconds. This is the moment when the physical laws we know today were not yet in effect. Space and time were in a highly distorted state. Temperatures exceeded 10 K in energy, was so high that elementary particles could not exist. Inflation 10 to the power of -33 to 10 to the power of -32 seconds. The universe expanded at an incredible rate, increasing in size trillions of times in a fraction of a second. This expansion smoothed out inhomogeneities, making the formation of large structures possible. Early hot stage 10 to the power of minus 32 seconds to 380,000 years. The universe was filled with quarks, gluons, and other elementary particles. Gradually, the first protons and neutrons began to form, from which atoms later emerged. Recombination and the first radiation 380,000 years. The temperature dropped to 3000 K, allowing electrons to fuse with nuclei to form the first atoms, mainly hydrogen and helium. This moment marked the birth of the cosmic microwave background, the first light of the universe that we can observe today. How did stars and galaxies form? After the Big Bang, the universe gradually cooled down, allowing gravity to begin its work. The slightest irregularities in the distribution of matter became the places where, over time, the first stars and galaxies began to form. The birth of stars. The collapse of gas clouds. Under the influence of gravity, giant clouds of hydrogen and helium began to contract, forming stars. In the core of each star, thermonuclear reactions ignited, turning hydrogen into helium and releasing massive amounts of energy. Supernova. When the first massive stars ran out of fuel, they exploded as supernova, ejecting heavy elements such as carbon, oxygen, and iron into the surrounding space. These elements became the building blocks for the formation of planets and even life. The formation of galaxies. The merging of small structures. Small gravitational clusters of matter merged to form larger galaxies. Different types of galaxies. Elliptical, spiral like our Milky Way, and irregular galaxies began to form from these primary clusters. The birth of our solar system. About 4.6 billion years ago, the formation of the solar system began in one arm of the Milky Way. This was due to the collapse of a giant molecular cloud from which the sun and planets formed. Stages of solar system formation. Protoplanetary disk. The rotating disk of gas and dust around the newborn sun was the site of planet formation. Planet formation. Inner rocky planets, such as Earth, formed from heavy elements. Outer gas giants, such as Jupiter and Saturn, formed from lighter gases. Earth and its uniqueness. Earth happened to be at an ideal distance from the Sun, in a habitable zone where water can exist in a liquid state, which was a key factor for the emergence of life. Interesting events and discoveries. Cosmic microwave background. In 1965, Arno Penzias and Robert Wilson accidentally discovered the cosmic background radiation, a faint noise left over from the first moments of the universe. This discovery confirmed the Big Bang theory. Gravitational waves. In 2015, scientists first recorded gravitational waves caused by the merger of two black holes. This discovery confirmed the predictions of the theory of relativity and was a revolution in astrophysics. Studying distant galaxies. The Hubble Space Telescope has revealed galaxies that formed several 100 million years after the Big Bang. These observations help us understand how the structure of the universe originated. Baryonic acoustic oscillations. Traces of sound waves that propagated during the early stages of the universe have been recorded in the large-scale structure of galaxies. This gives scientists data about the density and distribution of matter. why it's important. The Big Bang story is not only an account of the origin of stars and planets, but also a fundamental question about our place in the universe. That's why this topic is so important. Scientific understanding. Studying the early universe helps scientists test the fundamental laws of physics. Observing the cosmic microwave background and studying gravitational waves provide insight into the nature of time, space, and matter. Philosophical questions. Why does the universe exist? What is its meaning? Are we the result of chance or part of a grand design? Technological advances. The study of the origin of the universe has spurred the development of technologies such as space telescopes and particle detectors, which are finding applications in other fields as well. Current research. Scientists continue to unravel the mysteries of the Big Bang. Space telescopes. Observatories such as the James Webb Space Telescope study early galaxies to understand the process of their formation. Large Hadron Collider, CERN. Particle experiments help recreate conditions similar to those that existed just after the Big Bang. Gravitational waves. Their detection confirms the predictions of the theory of relativity and helps explore moments inaccessible to light observations. The mysteries of the Big Bang continue to fascinate the minds of scientists and ordinary people. It is not only a story about the past, but also a key to understanding the future of the universe. Knowing how stars, galaxies, and our planet came to be allows us to feel connected to something majestic and incredible. By exploring the story of the Big Bang, we not only come closer to understanding our origins, but also open new horizons for future discoveries. After all, every glimpse of the starry sky is a reminder that we are part of an amazing and vast cosmos.